Hey, thanks for joining everyone. Here at Blue Glow Electronics today, we are going to get back to our audio tube amp 101 series. Much overdue and much anticipated. I've gotten a lot of emails on the series. I started back in August of 2015. People asking when I was going to get back to this series. So finally broke down this morning, and we're going to create a video. Hopefully make a bunch of them this fall and winter as it's too dark and cold out to do anything in the evenings. But it's about 4 a.m. in the morning here. I'm up early, and I thought I'd just spend some time doing this before the family got up today. So here we go. If you'll remember back, we started out with episode 1, kind of an intro. I told a little bit about myself, laid out a syllabus. I think that syllabus will continue to evolve and change as we go into this, but anyway, we rolled then into EE Math 101, then voltage, current, resistance, and then I thought, wow, there needs to be more done on resistance, so I did a deeper dive on resistance. Then we kind of covered parallel series circuits and what a voltage divider is all about. From that, I broke off into kind of AC theory and varying waveforms, taught you a little bit about audio signals and how those are varying waveforms. And then today I've decided we're going to roll into an episode called Power. It's all about what in the audio world is power, and how do we measure it, etc. So let's dive on in. Okay, let's dive into power a little bit. What power is, if you kind of get to a physics class, they'll teach you it is a measurement of a rate of doing work measured in watts. And power, the thing you're probably most used to in life is the power rating of things like light bulbs. 100-watt light bulb, a 40-watt light bulb. The little light bulbs on your Christmas tree may be like 1-watt bulbs. The lights in a night light might be 7-watt bulb. But the kind of the gist of what you've been taught through life is the more power, in other words, the higher the wattage rating, the more that it will do, the more light it will put out. Similarly, like a soldering iron, soldering irons come in terms of watts. A 35-watt soldering iron can't put out as much, I'd say, heat and energy into whatever you're trying to solder as, let's say, a 70-watt soldering iron. So just a general principle holds true too. You turn the volume up on your amplifier, and if it's putting out 1 watt, the volume in the room will be fairly low. If you're putting out 100 watts, the volume in the room will be very, very loud. So this measurement of watts is kind of important to audio people because, one, they want to know how many watts their amplifier will put out, or they may want to know at how many watts does the distortion get too high that within their audio signal that it no longer sounds like the original source. So there's a lot of reasons you want to measure the output of something as it relates to audio. So if you roll back into a few episodes, we did something called Ohm's Law. It was just a basic theorem that had a relationship between 3 different things, between voltage, current, and resistance. And Ohm's Law basically had a math equation here that says voltage is equal to the current flowing through something times the resistance that something has. So a good example here is if we had 1 amp of current flowing through a 1 ohm resistor, voltage was equal 1 times 1 equals 1, right? And then you'll remember we talked about you can flip these equations around. So, V equals I times R is the same equation as I is equal to V over R. You've just kind of done some algebraic manipulation of the formula. Same holds true with R is the resistance equals voltage over current. It's just another algebraic manipulation of the same formula. And we can use either one we want to use to try to figure out what we have based on which variables we have versus, which one's a variable, which constants we have. If we happen to know the voltage and the resistance, then this is what we're going to use. We're going to use voltage and resistance, and we're going to figure out the current. If we happen to know the voltage and the current, and we're trying to figure out the resistance, we'll use this one. And similarly to Ohm's law, there is a power law that exists. And what it says is the amount of power measured in watts is ultimately equal to the voltage through something times the current. The voltage across something times the current going through it. Well, if you kind of get algebraically into this formula and substituting elements of it into this formula to solve for other things, you can also figure out that power is equal to current squared. In other words, current times current, the same amount of current times the resistance. Another way of looking at it, the one we will use in audio measurements almost 99% of the time, is P power is equal to voltage squared. So if you've got 2 volts, 2 times 2 is 4, divided by the amount of resistance. And this is a key note here, where V is a DC voltage, and we'll talk more about that comes up. But I've circled this in orange for a very good reason. This is really the formula you need to remember. Power is going to equal to V squared over R. You'll use it a lot on your workbench if you build an audio workbench. And up here you can kind of see here an amplifier, a speaker. Well, the speaker will be the R, right, the resistance, and the current flowing through the wires to the speaker. That's how you would get your current. And then the voltage measurement. So in other words, you put a probe or a set of meters across from these 2 wires right here. That's where you would get your voltage. So if you got a bench test set up, you've got everything you need here to figure out the power this thing is putting out. Okay, so if we put an oscilloscope probe across the output terminals, we could measure the waveform, and it would likely look like something down here on the left on your oscilloscope. And you would see this sine wave kind of oscillating back and forth. And it's really easy to measure then. You could say, hey, this is a 1 volt peak signal. Or you could say, hey, this is peak to peak, which is -1 here plus the 1. In this case, you end up with a 2 volt peak to peak all the way from here. But for what we're doing right now, we're going to measure this and say, hey, this is a 1 volt peak signal. Okay. Okay, remember earlier I showed you that power equation and I said when V is a DC voltage. Well, guess what? We've got a sine wave here that's going up and down, varying constantly. It is not a DC voltage, but there's a way to get close to what the DC equivalent value of that signal is. And remember, DC is just a constant voltage going all the way across, right? And this sine wave is not a constant voltage going all the way across. But one way you could approximate the value, let's say from this point in time right here, remember the x-axis here is time, up to this point in time, is you could chop off some of this up here and start filling in, almost like with sand, filling in a little bit over here, filling in a little bit over here, and you basically just start chopping off more and more and more till this top part is gone and it has filled in the sides till this thing is completely flat from this point in time right here, from there to here. And what that gives you, where that line is that you've been chopping off to fill in, that's your RMS value. Well, the beauty of a sine wave, because the math's already been done for us, is that value is 0.707 times the peak voltage. So if we know the peak voltage here of 4.3 volts, and we can multiply it times 0.707, we end up with 3.4 volts RMS. That would be the equivalent, somewhat DC value of this signal from here to here in time. Okay, if you're hanging with us at this point, you're doing great. So remember, I had where V is equal to DC voltage earlier. This point forward, I'm going to start saying where V is equal to RMS, because that's about as close as we're going to get as it relates to a varying waveform. So in this case, remember our RMS value here was 3.04, and the power equation says voltage, which in RMS, so 3.04 times 3.04. Then we got to divide it by the load here, which is an 8 ohm load, divided by 8. So 9.24 divided by 8 is equal to 1.1552 watts. So we'll round that to just say basically 1.16 watts. Okay, that's pretty simple math, and using the RMS value, which was pretty simple to get to, we have now figured out that if this thing is sitting here and you measured the voltage across here and you ended up with 4.3 volts peak, you did the math, it kind of got you to, hey, that's 3.04 volts RMS, and you used this equation, did the math, all of a sudden you know how much power this thing is delivering to this speaker. And not to confuse you, but there's another formula that's useful, and it's basically using just the peak instead of figuring out RMS. And it is basically power is equal to voltage squared, right, divided by resistance times 2. Okay. So in this case, you would say 4.3 times 4.3 divided by 8, the value of the resistance, times 2. So 4.3 times 4.3 is 70.56 divided by 16. We end up with 1.15 watts. And if you remember on the previous slide, we ended up with 1.16 watts. So this is just another formula that'll get you close to figuring out the value if you don't want to go through the computation to get to the RMS voltage. But both of these really just apply really well when it's a sine wave. Let's jump to the next one. Hopefully you're hanging at this point. I'm going to take you into some deeper territory here, so hold on tight. So I showed you two different formulas, right? V squared over R, where V is RMS, or V squared over R times 2, where V is equal to peak. This is key. However, both of these are approximations. And you may say, well, why are they approximations? Well, we've got to jump to the next slide to figure that out. All right, remember here, V in a DC circuit, this is a battery or a power supply or something that is constant. Feeding current into a resistance, which, by the way, is constant. If you buy 8 ohm resistor, it is 8 ohms now, it is 8 ohms always. If you buy 100 ohms resistor, it is 100 ohms now, 100 ohms always. There's some exceptions to that. Over time, some resistors break down, etc. But that's over 50 years, not something we'll worry about here. But here's the statement. So with DC voltage and current both are constant. So I'll admit, when you first apply the battery here, there's an inrush current that takes just a second. But once this thing stabilizes after a time constant of just typically a few microseconds, the voltage is constant, the current is constant, the resistance constant, right? Here's another key thing. These things are in phase with each other. So if you measured the voltage at a point in time and the resistance at a point in time, they would be basically in sync with each other at that point in time. And you'll see more what I'm talking about here in just a second. But this is what happens in a DC circuit. All right, so over here on the left, remember when you hooked the battery up to that little circuit, it took just a little bitty bit, maybe a few microseconds for the circuit to stabilize. But once it's there, everywhere from this point of time forward, the current and the voltage are kind of constant, right? And they're in sync with each other. However, in an AC signal, this is where it gets crazy. Both the voltage is varying, and if the load that you have the signal going into is not purely resistive, these things get out of phase. So we haven't learned yet about inductors and capacitors, but one thing you will learn about them is they are reactive devices. And what that means is their characteristics change with frequency. And how that plays out for us here is like this voltage may be doing this, and the current here may be lagging it by a certain amount of time. and typically that gets measured in degrees. But save that for another episode. What you got to realize here, though, is a speaker is not a resistive load. It is an inductive load. And when you're playing through a speaker, the current and the voltage are out of sync a little bit, right? So let's just pick a point in time, right? Let's pick this point in time right here where my cursor is at. At that point in time, voltage and current are in sync with each other. They're in phase at that moment in time. You could put a meter right there and measure it, and that would be something you could then plug into your power formula and use. However, we're trying to measure power over time. Well, look at this point in time right here. The voltage may be positive, but the current may be negative at that point in time. You get into another point here where the current is flowing forward, but the voltage is actually negative. It's a really complicated topic. You just have to trust me on this. But the reason I'm pointing this out is because what I'm saying here is this is what happens when the signal is not resistive. Things get out of phase. Oh yeah, by the way, the amount of resistance or inductance in the case of a speaker, the reactive load, it varies constantly in a speaker. So if you had an 8 ohm speaker and you were playing it, as that speaker is responding to the voltage applied to it, it may start out as an 8 ohm load, but it may swing all the way up to a 12 or 15 ohm load, all the way down to maybe a 3 or 4 ohm load while it's playing. So not only is your voltage and current varying here as you're applying a sine wave to it, when you're playing through a speaker, your load is varying constantly as it's playing. Which, what does that mean for us, and why am I telling you all this? It makes it really hard to measure a signal using an inductive load, i.e. a speaker. Thus, when we are bench testing, we use 1, a pure sine wave. We try not to use audio off of our iPod or iPhone or whatever when we're trying to measure audio output, power output. It just doesn't work out well. We use a sine wave. We also go and buy non-inductive resistors. So in other words, you buy a resistor right here that is non-inductive, specifically made to be non-inductive. I will tell you that some resistors out there, especially wire round resistors and other types, they have some inductance to them. But if you're using them in a DC circuit, you don't care because inductance doesn't come into play in a DC circuit. Whereas in an audio circuit, it does. So my bench setup, I bought 2 of these Dale. I've got 250 watt, 8 ohm, 1% resistors are what I'm using inside of it. I've got 2 of them in it, 1 for each channel, using a B&K Precision audio function generator. But this is a pretty high-end one, couple $100. You could buy on eBay maybe a $50 or $60, $75 function generator that would produce a nice sine wave. This one just happens to have a frequency readout and tells me that, and it's all built in together, so I kind of like that. But you can get a much cheaper function generator and generate a sine wave. And then you just need a basic oscilloscope. Now, I will tell you, not all oscilloscopes display here. Like this one is set on channel 1. It is reading the peak-to-peak voltage at 4.47 volts. Or you could set it to read the peak voltage here, and it would tell you that. Not all oscilloscopes do that. The further back in time you get, they don't have a digital display like this. Some of the more newer modern ones will have these displays. So you can get you a $300 Rigel oscilloscope, pretty modern one, and it'll display all this for you. So not a ton of investment. So what if you crank up your iPhone or iPod or whatever audio source you have, plug it into your amplifier, and then you run it and you put your oscilloscope across the leads going to the speaker, and this is what you see, because this is what a typical audio signal looks like. Well, first off, a couple things about it. A true audio signal, it's difficult to read the peaks. Where's the peaks? Where's the valley? I don't know if that to that is the peak to peak, or is that to that to peak. Well, it's because it's always changing. When I'm talking right now to you, my voice coils are vibrating and they're causing this type of signal. A true audio signal is typically into an inductive load. You're into a speaker where current and voltage are changing and out of phase constantly. It makes it pretty darn hard to measure power output. So what it takes to do that, you need some type of device that basically does samples. It measures here and here and here and here and here and here. Thousands of samples across this screen, if not hundreds of thousands of samples across this screen. And then it has algorithms it uses to to average all these samples together, and then it'll produce a power signal for you. So a good example of that might be a meter that can actually measure power output. I'll show you one of those here in a second. And it's doing a lot of mathematical computations to get to what the power output is in this thing at that point in time. Okay, there are power meters out there on the market. This left one was an older realistic audio power meter, probably $100 or something. This one on the right's a Macintosh power output meter, probably $1,000 or more. And then over here is just a simple little circuit you could buy and build yourself. But you kind of get a sense here of what's going on. You got some some logic chips here. And what are those logic chips doing? If you come back to this, they are sampling. They are taking little bitty snips of the signal all along the way. Then they're doing a little bit of math to them and calculating, and then they're displaying them here, either on the signal meter or via a number of lights lighting up. So somebody would buy a little circuit like this and build it inside their amplifier so that on the front of the amplifier as it's playing, it would be displaying how much power output the unit is producing. So basically just a little unit. You don't need the oscilloscope because you don't need to display it. You're displaying it here via LEDs, but this is a good way of measuring audio output at this point. And finally, we're going to do some real world testing is what we're going to go do. This is my bench. If you'll notice, I've got the audio generator signal source here up, feeding down into typically whatever we're going to measure the output of. The output then goes up into this dummy load setup that I've got right here. And you can see right there, you can see on the top of it, that's one of those Dale resistors right there. And then across the outputs of that Dale resistor right there are feeding out into these BNC ports. It's feeding out of there. If you'll notice the little red wrapper right here on that wire, it's the same red wrapper on that wire we're feeding into the oscilloscope here. And then we can use our oscilloscope to figure out peak measurements. And we can use that and a little calculator to get to the power output. So let's go jump over to the bench and do a little bit of real world testing. Okay, one last little thing before we jump onto the bench and do some real world examples. We'll wrap up episode 7 here on power, and episode 8 I'm going to do that one next on capacitors. So hopefully in the next week or two. Stay tuned, and let's jump over to the bench and do some real world scenario here with testing power in an audio amplifier. Okay, we're over here on the bench today. And what I've got turned upside down here that I'm actually working on right now is a Macintosh 225 amplifier with 7591 outputs. I thought it would be since I already had it on the bench, I was working on rebuilding some aspects of it. It'll be a great unit to end up showing you what's going on here. So first and foremost, I'm feeding out of the audio oscillator. In this case, it's called a function generator. This thing will go from 0 to 4 megahertz, and we don't need all that. We just need kind of 0 to about 20 kilohertz to do audio stuff. So right now I've got the setting on 1K here, and that is at 1.04, so 1 times 1K. We've got a 1 kilohertz, and we've got it set on sine wave up here. 1 kilohertz sine wave, and I can adjust the amplitude of that sine wave with this knob right here. And we are feeding that down here into this little thing here that converts mono into stereo here, this little adapter. Feeding it down and into right here. These two jacks feed into the amplifier. So basically I'm feeding the exact same 1 kilohertz signal into both sides of this. Kind of coming out the other side of the Macintosh amplifier right here with these banana jacks. They feed up and into this dummy load setup right here. So two Dell 250 watt 8 ohm resistors. You can see them mounted up in there. And then paralleled across those are these outputs right here. So basically if you connect something up to this device, you're measuring across that resistance right there. And you can see I'm coming out of this then with the red connection here, feeding over, and the wires kind of snake around, but it brings you into the oscilloscope where you can watch this nice little pretty sine wave that we've got going on. And this is a Tektronix 2246. It's a more modern, but still a cathode ray oscilloscope. But the reason I call it modern, it's a digital oscilloscope. Has the ability to display on screen right here, as you can see, kind of some digital aspects. You can go here and click voltmeter, and then you can pick something like peak to peak, and it'll tell you the peak to peak voltage. You can say voltmeter, tell me the positive part of it there. You can tell it to tell you only the DC component, etc. You can also do other things like time right here and 1/2 and then you can move the display over, and you notice I got it in the bottom of this peak right here, and you can move the other one over to right here in the bottom of that peak, and guess what it's telling me? It is a 1 kilohertz sine wave. So these scopes like this are pretty neat. This is a more modern Rigel DS1040 to do the exact same thing and much more. I just happen to prefer the kind of the clean sweep of the old analog oscilloscopes, but we'll go back to voltmeter. We'll go to positive peak here. And what are we reading here? We've got about 7.20 volts. It's jumping a little bit here and there, but 7.20 volts on the actual, and that's a peak. That's just from the center up to the top here. Remember, peak. And so let's come down here and do a little math, okay? So if we've got 7.20, by the way, this is a HP 11C calculator. I've had this thing since I was in electrical engineering school in the 80s, and these things were kind of the standard back then. You know, much more fancy digital calculators that can do all sorts of graphing and whatnot have came along since. But you still see a lot of electrical engineering fans and kind of audio guys still using these old HP calculators. They use a function called reverse Polish notation, so if you try to follow what I'm doing, it'll probably lose you. But basically, we're going to go here, and on this thing, we're going to say we've got 7.20. We're going to enter that into the register, and then we've got to multiply that times 0.707. We're going to enter that into a register, and we're actually going to hit the times to enter that one. And what does it give us? 5.094. So what is that? Remember, the peak voltage times 0.707, that gets us to 5.09 volts, right? RMS at this point. Now, interestingly, also feeding out of the dummy load here, I've got a blue cable here, and it feeds up and around, and where does it go? It comes back around and feeds in right here. And this is a Fluke 45 digital multimeter bench type, and it is it's a true RMS meter. And guess what it's reading on volts AC? 5.015 volts. So it lines right up with the calculations we did based on this. So, you know, it's easy for me. I can just kind of glance up here and see this number. And then if you'll remember the math I told you, right? So once you know the RMS voltage, right, you can do what? You can, in this case, we can take that number and we can store it, and then we can square it. So we're going to do that, and we get 25.9122, and we're going to then divide it by, and if you remember, you could do V squared over R. R is 8 ohms here, so we divide that out, and we end up with 3.23 watts of power that this thing is putting out right now at this 7.25 volts peak. Alright, I thought I'd show you something else interesting. Right now we're sitting at 2.24 volts RMS and 1 kilohertz sine wave out. And you can see here 3.4 volts peak. Well, I'm going to crank this thing up using the little knob here. As you can see, as I turn it, up we go. So this thing will go up and up and up. I'm running 17 volts peak right now, 12.38 RMS. And I keep going and I keep going and I keep going until right there. You see what happened to this? Let me pull the signal down a little bit. Watch what's happening to the top of this signal. See, it's starting to flatten out. See how it does that? Well, you're going to want it right before that. Okay, right there. And if you'll notice, it did the same thing on the bottom here. If I turn it up, just see it starting. And that's good, because when you got both the top half of the signal and the bottom half starting to peak at the exact same time, it means that your push-pull configuration in this amplifier is very symmetrical. So let's push it here until it just starts to clip just right before clipping. Right about there, I think we're at 19.85 volts or so, okay? And we can look up here and we can see that that's 14.20 volts RMS, right? Come down here to this thing, since we know the RMS voltage of 14.2, right? We store that, we're going to square it, so we put in 2 square, then we get back 201.64, right? And then what we got to do, we got to store that, we got to divide by 8 ohms, and bam, look at that, 25.20 watts output this thing is putting right when it's starting to clip. Well, this is a Macintosh 225 amplifier right here. The 25 in the 225 stands for, it is a 25 watt amplifier. So it would make sense that at 25.2 volts, it's starting to clip. So that's just another thing you can use the power output or the voltage measurement here to do, is determine maximum power output before an amplifier starts causing distortion. I'll jump you over and show you one more thing. Okay, another way to go about all this is I've moved the connection out of this jack right here, and I've put it into the output of the HP8903 audio analyzer. And if you'll notice here, I can then tell it like amplitude 0.15 volts, and it starts putting out a nice little sine wave over here. And if I it'll tell you the AC level here in RMS, which is 7, right? If you look up here, pretty darn close, 6.97. You can also measure distortion right here, 0.12% distortion on this thing. And then this thing also has a special feature. You can hit special, 19.0 special, and the reading right here will tell you that that is 6 watts of power output. So you can kind of get all that in one nice little box here without having to do tons of math or having an oscilloscope. But honestly, I could not get by without an oscilloscope. It is just too tough to do so. It's because you got to watch the waveform. What if your waveform was looking like that all the time? Something's wrong. I've got a bad connection right here. And I was just wiggling, but just likewise, you can hear both channels as I turn them on or off up here. But one last little thing I'm going to show you. And for the final part of our video, I'm going to play a little music here. Let's see. Watch. You stop the music, it stops. Now, you tell me how to measure the peaks of that. And this thing's trying, it's bouncing all over there. It's trying to do an average here. You can see going blind, going up and down. You can see up here, it's just bouncing all over the place. And it's the reality is, I'll put it on silent, putting one to the dummy load. As you can see here, as I increase the volume, it kind of increases the intensity there. As I bring the volume down, it goes really quiet. Crank it back up. But you get the concept. That's just audio. just extremely hard to measure. It's why we do bench testing with dummy load, non-resistive. And then we also use a sine wave, something predictable, something we can measure against. The downside to measuring audio with just sine waves and whatnot is you don't always get the full dynamic range. You know, can this thing play something at 20 kilohertz? Can something play something down at 50 hertz? But we're going to cover that in some future episodes. I just wanted to get you the essence of reading power measurements today. Hope you learned something. If you got questions, post them. We'll answer. And thanks again for watching, everybody. Hope people are happy I'm bringing this series back. And if the excitement's there, I'll keep cranking them out. Thanks.